All right, so like I was saying yesterday, back in middle school, you guys have had seen something called eighth man. All right, so A equals P equals E was what you had for it. All right, and so does anybody remember what the A stood for? Not answer.
Atoms.
Not atoms either. Atomic number? You guys remember that? Okay. So atomic number is equal to, do we know what P is? Protons, good. And then electrons, good. All right, and then what do we know about protons and electrons? Or what do we remember?
Protons are positive.
Perfect. Protons are positive, electrons are negative, all right? So what you'll see me kind of write shorthand is that protons, I'll put a P with a little plus, and I'll put an E with a little minus, all right? A lowercase and lowercase, all right? So this right here, this statement, atomic number is equal to protons is equal to electrons, is only true when neutral. And you guys have to consider that, because now you guys are in high school, so we're not in middle school anymore. Everything was neutral in there, right? And so now we're going to be dealing with things that have charges, so an imbalance of them. Okay, so we'll talk about that later. The other part of eighth man was man, right? So we had M minus A equals N. Anybody remember what M stood for? Mass, good. And we're going to get a little more specific. It's called a mass number because it's not your average atomic mass, so it is not the number that's on the periodic tables, all right? It is actually more of a counting number. It's going to be a whole number, okay? No, not yet. Those are going to be the group numbers. Yeah, not yet. All right, so mass number minus A is still atomic number. What does N stand for? Neutrons. Neutrons. Okay, so neutrons. Okay, what do we know about neutrons? Do they have any charge? No, they're neutral. Okay, so they are a 0, or I will put an N with a little 0 like that. Okay? Yeah. Yeah, sorry. Okay, so atomic number. What I want to change this one or write underneath it is I want you to write the word protons again, because what's going to be important is you being able to really, whenever you're seeing an atomic number, you know it's protons. And whenever you see protons, you know that's the atomic number. Those protons are so important. They never change. They're what define each and every element up there. Because if you look at a periodic table, you have them in front of you, right? Every single element on there has a different number. No number repeats itself. That's because we're talking about those protons in the nucleus. That's what defines it, okay? So it gives it identity, all right? And then the electrons give it its reactivity, and then the neutrons just give it some mass, and we'll talk about isotopes today as well, all right? All right, so going back over to the left-hand side, okay? These things, protons, electrons, and neutrons, these are called subatomic particles. Subatomic particles. So your protons, your electrons, and your neutrons. Okay? Atoms of different elements have different numbers of protons. So then, obviously, the next one, atoms of the same element have same number of protons. Kind of redundant, right? Just keep repeating itself. All right. Atomic number is going to be the number of protons in the center of an atom. Does anybody know what the center of an atom is also known as? A nucleus, yeah. Okay. Why is the atomic number used to identify elements? Like my grammar there was great. It's great stuff. So why is the atomic number used for that? Well, because the atomic number is protons, and protons never change. And that right there, that is a key statement. That is a big thing that you can hold on to for the whole year. Okay, and I always like to ask that. All right, I asked something about the protons. Protons never change. They define who we're talking about. All right, in the periodic table, elements are placed from left to right in order of, so looking at your numbers that are on the periodic table, what are the numbers doing from left to right? They're increasing, yes. So in order of increasing atomic number, an increasing atomic number, okay? Because all atoms are electrically neutral, the number of protons equals the number of electrons, okay? The number of protons is going to equal the number of electrons. All right, I can zoom in too. I see you guys taking pictures, my bad. All right. Okay. So this next little spot, this is just showing you what every single square looks like on your periodic table, right? So you see here, the atomic number is the big number that's usually on the top. Sometimes it's on the bottom. It just depends what periodic table you're looking at. Okay, but you have your atomic number. That's the one that goes up by ones. Then you have this fancy little decimal one down here. That's your atomic mass in AMU. So we're going to see that this is actually an average atomic mass. Which is why at the beginning I said mass number. Mass number versus average atomic mass. So this one has all the decimals. But I did want to make sure that you understood what AMU is. AMU stands for atomic mass unit. Right? That is going to be the unit that you're using after your numbers when calculating for now. Okay? It's an atomic mass unit. So we're saying it's something that's measuring the mass in an atom. Okay? Eventually we'll get to grams and all that good stuff. All right, so next we have the simplest atom is hydrogen. We're going to talk about this real quick. It only contains how many protons? One. Good. You could get that from the atomic number, right? All right, so what this is, this little table down here with the fancy names on it, okay, this is representing your isotopes of hydrogen. So before we go to that, let's go ahead and fill out these couple lines down here. So isotopes, this is a key word. This is one of your vocab words. You shouldn't know what that, or you probably haven't heard of that one yet, okay? But isotopes are atoms of the same element that have different masses. Okay? This is because they have different numbers of neutrons. Okay? So, ultimately, your neutrons, we already talked about, neutrons don't really contribute anything to the atom. They're not giving it a charge or anything like that. They're just like extra mass. So, just to kind of put it in perspective, it's kind of like fat, right? So you have some hydrogens that are going to have more fat on them and some that have less fat on them, right? But it's still hydrogen. Just like us, we lose weight, we gain weight, we do both, right? That's what life is. But we're still the same person, right? But we just have that extra fat or no fat, right? So think of neutrons like that, and it'll kind of help you out a little bit. So it's still the same element. You're just giving it an extra mass, all right? The stuff that doesn't contribute any charges. All right, so isotopes containing more neutrons have more mass, that makes sense, but have the same chemical properties, meaning it is still who it is. Okay? So let's remind ourselves, mass number. So in man, up at the top, right? Mass number is the number of blank in the nucleus of an atom. What makes up our mass number? Neutrons is 1. What else is in the nucleus? Protons. Protons and neutrons. Okay. Are you guys okay with me using shorthand here? So I'm doing protons, P plus, right? And then neutrons with little neutral symbol, okay? Okay. So now that we have that, now let's look at this little table. So this is all talking about hydrogen. So no matter what, the element is hydrogen. It has chemical properties of hydrogen. However, these 3 different types of hydrogens, these different isotopes of hydrogens, have fancy names. Those are the only ones that have that. All right, so protium, we have an atomic number of 1. So I'll just tell you, you have a mass number of 1. How many neutrons do I have? 0. Good. So protium is just a proton. That's kind of what we're calling it. Okay. So you have a proton and you have an electron because it has to balance it out, but you don't have any neutrons. Nothing else in that nucleus. All right. So we have that number of electrons going to be 1 because they have to balance out. All right. Deuterium. So this is going to be one that has 1 neutron. What is the atomic number of it? If they're all hydrogens. What's the atomic number of hydrogen? Still 1. Thank you. Good. 1. All right. So what is my mass number? Remember, you add them together. Yep. 2. Good. How many electrons do I have? Still 1. Good. Electrons are very, very tiny in comparison to our protons and neutrons. That's why we don't really count them towards the mass. They contribute a little bit, but it's like so tiny that it's pretty much negligible. All right, especially when you're starting out in chemistry. All right, tritium. What atomic number does that one have? Still 1. Good, we caught on. All right, if the mass number is 3, how many neutrons did I have? 2. Awesome. All right, so 1 plus 2 equals 3. That's why we got that. And number of electrons is still going to be 1. This whole percent abundance, we're going to get to that in a second, okay? But it's going to be how we get our average atomic mass. You got to use how abundant they are in nature. All right, so what is hyphen notation? Okay, so hyphen notation. What this is going to look like is you're going to use the symbol, the chemical symbol or name of an element written with a dash and the mass number following it. Okay, so the examples that we just had above there, for protium, we would have had hydrogen, and we would have put a 1 after it. We had hydrogen with a 2 after it. I could turn around and say carbon with a 14 after it. Carbon 14. Okay, so things like that. Oh, sorry, I guess I should have given you an example of writing out the name. So carbon 14. There you go. All right, so that would be the other way you could write it. So name or symbol. All right, so hyphen notation is probably the easier one. You just have to write the mass number, okay? You need to be able to read that and know what this number is. That's your mass number, okay? All right, nuclear notation is the one that you will be using the most for me, okay? Nuclear notation is still going to be the symbol or the name of, no, I'm sorry, the symbol of the element written with the mass number in the upper left. Upper left made it a superscript. Okay, mass number goes in the upper left as a superscript, meaning above. Okay, so the superscript tells us our mass number, and the atomic number is your lower left, or the subscript. Okay, so mass number we're getting from protons plus neutrons. Atomic number we're getting from protons. Make sense? We're kind of repeating this over and over and over. So if you don't have it after these notes, no, I'm just kidding. But yeah. So how do we find the number of neutrons? How do we do that above here? We took mass number minus atomic number, which we know atomic number is your protons. Okay? There you go. All right. So we got what an isotope is. Okay. You guys are also, because you're advanced, okay, I already introduced you to your ions concept. Okay, it's something that we hit a lot more when we get into bonding, because then you learn about ionic bonds versus covalent bonds, those kinds of things, okay? But for now, ions is when we have a charge, okay? So how does that happen? How do these things have a +1 or -1 charge? Because they're imbalanced, right? What's imbalanced specifically? Exactly, protons and electrons. So far, we were dealing with those things being balanced, which makes it neutral, electrically neutral. If I tell you now you have a charge, that means there's an imbalance. So question, if I have a +1 charge, does that mean I'm adding an extra proton? Am I adding a proton? Okay. What did we write up here? Number 5. We put a star next to it. Protons never change. Never, never, never. The number of protons makes the element who it is. Okay? So ions is never going to be, you will have positive charges. It's never going to be about the protons being added to it. All right? It's always about electrons. So an ion will be a loss or gain of electrons. There you go. Loss or gain of electrons. Okay? All right. If we know electrons are negative, if I lose negativity, what happens to my charge, do you think? Positive, right? That's like a life skill right there. Like if you lose negativity in your life, you become positive. Get rid of the negative things, you get positive, right? And then if you gain a bunch of negative stuff, what are you going to, if you gain electrons, what happens? You become negative. Okay? All right. Hold on, because we got to write down, that's right. So how this applies to you for right now, when you're dealing with an ion, you're looking at an imbalance of your protons and electrons, right? Protons do not equal electrons now. So when you have that situation, which you will tomorrow on your page that you guys are going to have with the sub, okay? When they don't equal each other, you have to indicate that in the nuclear notation. So for example, let's do oxygen. So you guys all have a periodic table in front of you. So let's go ahead and write O for oxygen. Okay? All right. What number am I going to put on the bottom left? What number goes right here? Bottom left for oxygen. You guys, please don't stare at my face because it's not there. It's on your periodic table. So where is it? What's the number? 8. There we go. All right. So 8. So we put an 8 in the bottom left, right? Because that's our atomic number. All right, I'm just going to make up an isotope. I'm going to say oxygen 18. Okay? If you notice on the periodic table, is that what the mass number is for oxygen? No, right? It's 15.99999, which is about 16, right? So your mass numbers are usually going to be very close to it, but it doesn't have to be that number, all right? Because we are dealing with neutrons. Okay, so this isotope is oxygen 18. I made it up, so don't quote me on that one. All right, so if I tell you that you gained 2 electrons, if I gained 2 electrons, you have to show the charge in the upper right side. What charge are you going to put there? A negative, and then you got to tell me how many. A -2. I gained 2 negative things, so I'm more negative. So that right there, that's how you're indicating an ion. Okay? You write the charge up here. This is still atomic number, still mass number. Okay, so if we need to put labels, I would do that. That way you're not confused when you look at your notes tomorrow. All right, so this is your charge for an ion. This is your mass number, which I made up. And this was your atomic number. Okay? All right. If I took away 2 electrons, what would I have? +2. Good. All right. So let's go ahead and take a look real quick across the page at number 15 up here. It says, how many subatomic particles are in an atom of copper 64? Okay, copper 64. So I want to write my nuclear notation. I'm going to just be asking you, please write your nuclear notation down your page. All right? As you're doing these practice problems, write the nuclear notation. Get yourself in the habit of it. All right, so first thing we need for nuclear notations, we need our chemical symbol, right? So what's the chemical symbol for copper? Cu. Okay, Cu. All right, so what goes in the top left? Not 29. I asked that one on purpose. Huh? It is going to be the 64, your mass number. Okay? What's going to go in the bottom left? That one's going to be 29. Good. Okay? And then did I indicate anything about a charge up here? No, right? So I'd have to go out of my way to tell you it's an ion. I'll just tell you right now, this list right here, there are no ions. I probably should have put some on there, but it's okay. We'll deal with it later. So let's go answer these now. How many protons does copper 64 have? You're doing a great job. How many protons, you guys? 29. Good. Your atomic number. How many neutrons do we have? How do we get neutrons? Look right above it. Huh? Or at least tell me how we're going to do it. Good. We're going to subtract 29 from 64. So we're going to say 64 minus 29, 35. Good. So we have 35 neutrons. How many electrons do I have if it's neutral? Still 29. Good. Okay. All right. So I'm going to give you guys the next 7 minutes. No, 5 minutes. Get at least 15 through 19 done. Continue on if you get those done. But I have one more thing that I do have to show you before tomorrow. So we're going to go right back to the notes, but I want you guys to try a couple of those out on your own, and I'll show what the answers are for 15 through 19 after. Okay? So take about 5 minutes, and then we'll stop. Okay, so like I said, this is what the table is going to look like, so you can kind of see all of the titles across the top. You're still thinking the same exact thing, all right? So that's what you guys are going to get tomorrow. Here, where you see ion, what does that tell you you should go look at immediately? V who? The electrons. Yep, electrons, right? Because we already know it's chlorine, so you know what protons are. I would go look at the electrons, and then you're going to figure out what that charge is, right? And so chlorine, I believe, is 17, and so you would have a -1 charge, okay? But I'm not going to write that out because I need you guys to figure that out tomorrow. All right, so on the back of this page, flip it over. Okay. On the back of the page, we're going to use this little tiny spot up here to write this one out, okay? But basically what's going to happen with our isotopes, all right? When you are asked to calculate average atomic mass, that means that you are trying to figure out the number from the periodic table, all right? These are the steps. I'm not going to make you write them. I'm going to post them onto Schoology, and you can use those, all right? Yeah, because I won't have time to make copies before tomorrow. So I'll probably post them on Schoology, so look there, all right? But what we're doing, you read the question, note the masses of the different isotopes. Don't round yet. Don't round until the very, very end, okay? So you're going to write out this number that usually has like 4 decimal places. It's huge, okay? You're going to go ahead and write out the masses. You're going to change all the percent abundances into decimal form. Percent means out of 100, so all that you're doing is you're dividing it by 100 or moving that decimal 2 to the left. So 90% becomes 0.9. You're going to calculate abundance, the percent things, times the mass. You're going to multiply. So multiply, multiply. Those answers that you get, you add together. That's the periodic table number. Okay, so let's do this example so that you have one, and then you can rewatch this video tomorrow to remind yourself, and you'll be fine. So naturally occurring silver has 2 isotopes. We have isotope A with a relative mass of this. There's that long decimal that I was telling you about, and an abundance of this. Isotope B has a relative mass of that. Why didn't I give you a percent? Not because it's the same, but can we figure out the percent? Well, how many is in a total percent? 100, right? So you're just going to take your 100 minus your this percent. So you're not always going to have to do that. So let's just do that real fast. That way you have it. You're going to get 48.18. Okay, so isotope B is 48.18. All right, so now I'm actually starting the steps. All right, that was just, we got everything ready. We have percents, we have our masses. So we're going to take isotope A. Okay, notice it's silver, so I'm going to go ahead and use my chemical symbol. So silver A, that's all I'm going to call it. Okay, usually it'll have a number. But for now, silver A. We're going to have the mass of 106.9051. We have silver B. That one was 108.9047. Okay, so I noted my 2 masses. There they are. I'm going to multiply them by my percent abundances, but the percent abundances, we had to take that decimal and move it 2 to the left. So for this one, 2 to the left tells me 0.5182. For isotope B, we have this 48.18. We're going to move it 2 to the left or divide it by 100. 0.4818. I'm going to type those into my calculator. Okay, so big number times this, right? So when I typed it in, I got the number 55.3982. I went all the way to the 4th decimal place. I think there were more than that. Okay, but I'm keeping it consistent with what was in the question. The other one, when I typed it in, I got 52.4703. The last step, according to the things that I just had up here, okay, we calculated abundance times mass, add those numbers together, add together all the answers. So we're going to take those two answers, I'm going to add those two together. Okay, it looks like a lot of steps, I know. Just roll with it. You'll have the steps in front of you, so just do that. You will get 107.8685. So do me a favor. Go look at your periodic table right now. Did that match up for silver, Ag? Did that match up? Yeah. So that is how those numbers came about, okay? Whew, you guys did an awesome job. So